I see a lot of faces here, so welcome. So today, the main topic is how to analyze pair data. My name is Le-Rademacher, and I am an assistant professor in biostatistics. The lecture is sponsored by the Clinical and Translational Science Institute and the Division of Biostatistics. I have no financial interest to disclose. And if you need CME credit, please fill out the form so we know who to give the credit to. If you don't need CME credit, we would appreciate you filling out the evaluations so we can improve our future lectures. So even though the main topic today is to analyze pair data, before we're talking about analysis, I will go over some scenarios where you can obtain pair data. And then we'll talk about how to analyze just common types of data, numerical measurements, and categorical measurements. And then we'll wrap up with some concluding remarks. Yeah. So how do we get pair data? In a typical comparative studies, a simple design is to have two different independent sources to compare, to apply the treatment to, and then compare the outcomes using those two independent sources. If that's the design, then you will get independent samples. Okay? So in independent samples, there's no link between the objects from one group versus the other. For example, if you want to compare treatment, eye treatments for different subjects, so you have eyes from different patients, then you end up with independent samples. Or if you have two samples of unrelated individuals, then you have independent samples. Some alternative designs will actually, you can use some alternative designs that will give you dependent samples, which means that there are links between objects in one group with objects in the other. And some examples are if you compare treatment based on two eyes of the same patients, or if you use twins to study treatments, or siblings, compare before and after measurements. And in some cases, you can actually match individuals that are not related, and that's artificially linking them by certain characteristics. And we'll go through some scenarios of these examples. So like I said, the study setting is if you have two different treatments and you want to compare the outcomes. And by treatments, I use it very broadly. You can have two active treatments, A and B, or you can have one active treatment and a placebo or a sham device. Or you can have an intervention and control, which you don't do anything to that patient. Or you can have, looking at effect based on patient characteristics. So you can have male versus female, or older patients versus younger patients. So by treatment, this is very broad in this sense. And the typical hypothesis we want to test is the null hypothesis that there's no difference between the outcomes based on those different treatments. And the alternative is there is a difference in the outcomes resulting from those two different treatments. Okay. So some scenarios of possible designs. Let's say if you want to look at a prospective randomized trial comparing treatment A versus treatment B, or active treatment versus placebo, right? A typical design is you accrue, let's say if you want N patients in each treatment, so you accrue 2 times N patients and randomly assign half of them to treatment A and the other half to treatment B. If this is the design you use, you'll end up with independent samples. An alternative design is to accrue N patients, and you assign both treatments to each patient, but you want to do it in random orders, so you don't have a systematic bias. Okay, so if that's the design you use, then you will end up with pair sample. Okay, and the advantages of each of the design here, I only list advantages, but the advantages for this design, is contrast with the disadvantage of the other design. Okay, so if you look here, both of these designs will have advantages and disadvantages. They don't just have advantages, there's no disadvantages. So if you have an independent study design, it means that for a lot of outcomes, let's say survival, you can use independent sample, right? But if the outcome is survival, you can't really use the pair design, because if the patient died, you can apply the other treatment to the patient, right? So independent sample study is more applicable because you can apply it to more outcomes. And with treatments, certain treatments, it's not ethical to apply multiple treatments to the same patient. So in this case, you would want to use a independent sample design. Another advantage of the independent sample design is shorter on-study time. So you have to accrue 2 times n patients, and then you will accrue, n patients to one group and n patients to the other group. So you have parallel groups, and you can follow them on. Let's say if you need to follow patients for, let's say, a year, then after you accrue the patients, you follow them, both arms parallelly, for 1 year, right? If you use the pair study, it means you follow the patient for 1 year, and then have to add on some washout period, and then apply the next treatment and follow for another year. So you will end up with longer on-study time if you use a pair sample. Okay? So those are some of the considerations that you need to take into account when you design a study. So now if we look at the advantages of the pair sample design, you require fewer patients, right? Half of the number of patients in this case. So if per patient cost is a concern, this will cost you a lot less money because you only need to pay for half of the patients instead of 2 times n. And for pair design, you require shorter accrual time because you only need half of the number of the patients. And this is a special concern if the disease is rare. Let's say if you need 100 patients per treatment, and it's a rare disease that will take you a year to accrue 100 patients. If you use this design, if you use the pair design, you will need to wait 2 years to accrue. No, if you use the independent design, you will need to wait 2 years to accrue 2n patients, right? 200 patients. So that's the advantage of the pair design. You have shorter accrual time. And again, if you compare the outcomes of treatment from the same patients, you reduce the variability, so you don't have to worry about between patients variability when you compare the treatment outcomes. Yeah. So another possible scenario that we can obtain paired data is in prospective observational studies. Let's say if you want to compare outcomes from an intervention versus a control. Again, you can either accrue 2n patients, assign n to the control group and n to the treatment group. And then you'll end up with independent samples. Or alternatively, you can accrue n patients, then all of them will be assigned to the intervention. So you want to measure the outcomes before you give them the intervention, and then apply the treatment, and then measure the outcomes again after, and you compare the difference between after versus before, right? So that will show you the treatment effect. And the advantages and disadvantages for independent sample here is similar to the randomized studies. Okay, you have more applicable outcomes and treatments, shorter on study time, whereas the advantage of the paired study design is, again, the same. You require fewer patients, have lower per patient cost, reduce variability. And another advantage of the pair sample here is because it's an observational study, so you can't randomly assign patients to treatments. So if you use the pair sample, it will reduce the systematic bias. Let's say if you have worse outcomes on older patients, and if you use independent samples, what if you end up with more older patients in one group versus the other? Right? Then your outcome will be different, but it might not be because of the treatment itself, but it could be because of the confounding factor of age. Yeah. So that's an additional advantage. In randomized trial, this is not a real concern because you'll hope that by randomizing patients, that will balance it out. And then Another scenario where you can encounter pair data is retrospective studies or case control study. So you can, in case control, let's say from a large database, you can randomly select a sample and then classify patients based on their outcomes, right? And what you want to do is go back and look at their characteristics or exposure to certain factors of interest. And then you want to see if there's an association between the outcomes and the factors of interest. In that case, then you get independent samples. Or you can, let's say the database is really large and you don't want to include all the patients. Then you can select N patients with outcome 1, let's say patients who have the disease. And then you select N match patients without the disease. And you go back and compare the characteristics. So in this case, you get pair sample, but the pairing here is a result of matching. So it's artificial pairing because it's not natural, like two eyes of the same person or a set of twins. There's biological link there. In this case, you took two independent individuals with some common characteristics, and you're hoping that by matching in those characteristics, it will take care of all the confounding that you will get in the result. So the advantages here are similar to the previous scenarios. One thing that I want to point out is if you use independent samples, it is possible to estimate the covariate effect. For instance, when you do regression. Okay. Whereas if you use the pair sample, let's say if you match on patient's age and gender, in the model, you can't really put age and gender in the regression model, so you can't quantify the effect of age and gender anymore. So that's a disadvantage of pair sample in this case. Now for the advantages of pair sample, here is a smaller sample is an advantage. Of course, the advantage of independent sample is larger sample size, so it means the power is a concern, that this is an advantage, right? But if power is not a concern, then sometimes, let's say, you have to go back and collect additional information, okay? And let's say if it's a rare disease, you have a large database, and you have, let's say, 100 patients, 100 cases, and you have, let's say, 1,000 controls. If you need to go back and collect additional information, if you use the independent sample and you include everybody, then you need to go back and collect information of 1,100 samples, right? But if you use the match design, let's say you want to look at just one match control for each case, then you have only 200 patients total for the study, right? So you can go back and collect, you only need to collect information on 200 patients. So that is an advantage of the smaller sample size in that case. And again, reduced systematic bias is one of the big advantages for pair sample in this scenario. So, I said the previous scenarios, the pair sample comes from matching and is artificially linking the patients. So, matching is for every case you select a control that has similar characteristics, but you can also select more than one control for each case. So, it depends on what the study objective is and how many samples you have. So a lot of things go into consideration for designing a study. But the main thing I want to point out is for the independent, for a typical independent sample study, depending on the outcomes and the treatments, you can have an alternative design that will give you paired samples. Okay? So whatever the study design is, your analysis have to match with the design, to make the most out of the information that you get from the study design itself. Because you don't want to spend all this time thinking about the best design, and then in the end you just analyze it without considering how you designed the study. Right? So you don't use all the information. And so, like I mentioned, reasons for matching is to eliminate confounding factors and things that would associate with outcome. So to analyze pair data, I'm going to give 3 different examples here. The first one is to look at continuous variable that we can assume normality. So this example, I'm using a study published by Connolly et al. In 1998. The objective of the study is to determine whether there was a difference between visual outcomes of eyes treated with transcerebral biotherapy versus laser photocoagulation. Okay. So the study was designed as an extension of a randomized clinical trial that looked at patients, that looked at two different treatments. One is cryotherapy and the other is laser treatment for these children. And the outcomes of interest are the best corrected visual acuity, which is a qualitative measure. And the second outcome is the spherical equivalent, which is quantitative. So for this example, I'm going to use the second measure, the spherical equivalent, as the outcome. I'm going to illustrate the test here. So here's the paper. If you're interested, you can get this paper from the library. Okay, and the data. So here's the table with all the data that I extracted from the paper. And there are 25 patients here at the gender. You know, which eye get treated with cryo and which one get treated with laser therapy. Okay. And then these, this is the primary outcomes here. And then this is the outcome that we're interested in, spherical equivalence, from two different treatments. And then you can't really see all the details. I just want to let you know that the paper exists if you want to look at the example. How did I get that? Sorry. So before I go on, sorry, do you have any questions about the design and how you can obtain pair data? No. But you can ask questions later if you have any questions. Yeah. So here's the data again. And the hypothesis here is the mean difference between spherical equivalence of eyes treated with cryotherapy and eyes treated with laser photocoagulation is 0. And the alternative is the mean difference is not 0, right? So here we're looking at a two-sided test. And the testing method used for pair data with continuous measurement, and we can assume normality, is the pair t-test. And in this test, we use the significance level of 0.05, which is the typical values that people use. So pair t-test is applied to compare continuous measurement from two dependent samples. Okay, so here you actually look at data that you can pair up an observation from treatment A with an observation from treatment B. And the assumptions is the difference are independent and they are normally distributed. Okay. So the test statistics used here is a t-test. The test statistics is the ratio of the mean difference versus the standard error of the mean difference. And the decision-making procedure is if you observe a test statistic that is too large, then you reject the null hypothesis. If it's not, then you can accept the null hypothesis. And the inference is based on a t-distribution with n-1 degrees of freedom. So back to the example. Here we have 25 patients. Right? And you have the measurement for the cryo treatment and measurement for laser treatment. And so we need to calculate the difference between the spherical equivalence between the two treatments. So in this case, I use laser minus cryo. So here, positive difference means that laser has lower value. I guess it means it's a better treatment. Okay. Look at observation number 4. There's a missing value here, so we can't calculate the difference. Okay. And then 25, there are missing values for both treatments, so there's no difference. So for the purpose of this example, we would discard number 4 and number 25, so we end up with 23 observations. Okay. There are ways for you to obtain or estimate the value, the missing values, but that's not the focus of the talk. And so for the purpose of this example, we look at 23 patients with complete data. So the mean difference, so the mean of that column is 2.02, and the variance of this column is 10.74. So if you look at the test statistics, it equals 2.96. So it's a t-test statistics. 22 is the degrees of freedom, right? N minus 1, and we have 23, n equals to 23. So using the t distribution with 22 degrees of freedom, we get the p-value at 0.007, which is less than the significance level that we set in the beginning. So based on this, we can reject the null hypothesis and say that there's enough evidence that the mean difference between spherical equivalence after laser treatment versus cryo is not 0. Okay. And it's always nice to give a confidence interval. So here the 95% confidence interval of the mean is 0.61 to 3.44. Okay. So why do we have to use a pair t-test instead of a two-sample t-test? Here, I just want to illustrate that when you ignore the pairing and you use a two-sample t-test, you might end up with a different conclusion. Okay? So if you incorrectly assume that the two eyes of each patient are independent, and then you can do a t-test with 44 degrees of freedom. So this is a two-sample t-test, right? You see that the difference, the mean difference is the same as if you do the pair t-test, but because of the variance is estimated differently, you end up with a smaller test statistics. Okay? So in this case, the p-value equals to 0.14, which is larger than the significance level. So you end up concluding that there's not enough evidence to show there's a difference between the two treatments. Okay? So this is an example to show that if you incorrectly do the analysis, even though your designs say that the data will pair, then you might end up with an incorrect conclusion. And the 95% confidence interval, again here, includes 0. Okay, so that's enough. So what happens when you can't assume normality, or when the sample is small, and you can't assume that the mean has normal distribution, then you can use alternative methods using nonparametric testing. So for the second example, I want to look at the data published by Geffen, and it was published in the Quarterly Journal of Experimental Psychology. The objective of the study is to determine whether certain numbers presented in random order will proceed more rapidly in the right or the left visual field. So in this example, they collect 12 right-handed subjects. Right? Most people think, if you're right-handed, it means that you are quicker perceiving numbers on your right eye, right? Because it's your dominant side. So in this case, they want to test the hypothesis to see if you're right-handed, is that true that you perceive numbers quicker on your, based on your right visual field? And the outcome is the response time to to each eye recognizing the number. So in this case, a better treatment would, or the treatment in this case is right versus left visual field, right? So this is an example of characteristics that we consider as treatment. So here's the data. You have the response time for left visual field and response time for right visual field. And there are 12 subjects. Yeah. So to compare the response time here, because there are only 12 subjects, and in this example, we can't assume that the data is normally distributed. So we use a nonparametric test. So the hypothesis is the median of the differences in response time between left and right visual field is 0, and the alternative is the median of the differences is not 0. So I'm missing a not here. So the alternative is the difference is not 0. Okay. And the testing methods that can be used for this is either the sign test or a sign rank test. And again, we use a typical level of significance of 0.05. So first, look at the test using a sign test first. So again, the nonparametric test we use to compare numerical measures that we can assume normality. And the sign test, here we apply to dependent samples because this is single sample test. And the advantage is we don't have to assume normality for the differences. Okay. And the disadvantage is nonparametric test has lower power, so you waste some of the information without assuming the form of the distribution. And another disadvantage is if the distribution is really normal, you have less power, so you waste information. So the test statistics in this case is the number of positive differences. And if under the null hypothesis, if the median are the same between the two groups, then it means that you have half of the observations will have positive differences and half will have negative differences, right? And so you reject the null hypothesis if the number of positive differences is too large or too small. Okay. So here you say number of positive differences. You can also, it's the same if you actually look at the number of negative differences. Okay. Because of the symmetry. And the inference is based on a binomial distribution. Or if the sample size is large and you still can't assume normal distribution, then you can use normal approximation in this case. So back to the data. So we have the measurement, the response time for left versus right visual field. And the difference here is just the difference between those two measurements. And so for each difference, we just look at the sign. We don't care about the magnitude of the difference in this case. In the sign test, all we want to look at is the sign of the difference. So for the first 9 observations, the difference is positive. So it means that the left visual field requires higher response time, right? So, and then for the 10th observations, the difference is negative, and then for the last 2, the difference is positive. So in this case, out of 12 observations, 11 of them have positive differences. Right? That's a large number of differences. Okay? So the p-value in this case is, because it's a we're looking at a two-sided test, the p-value is 2 times the probability of having 11 or more positive. Okay. So the p-value here is 0.006, which is less than 0.05. Okay, so in this case, we reject the null hypothesis and conclude that there's significant evidence that the median's difference is not 0. Okay. And you can obtain the 95% confidence interval of the medians. Any questions? Okay, so the next test is the sign rank test. So before we go into the sign rank test, so here again, I just want to make sure. We only look at the sign, we don't care about the magnitude or the rank of the difference, right? Another test that we can use is the sign rank test, and as the name suggests, here you actually take the ranking into consideration. Okay. So in this test, you actually rank the differences first, ignoring the sign, and then you'll add the sign to the ranking later. And the test statistics is calculated from the sums of the rank of either the positive or the negative sign. And again, if under the null hypothesis, the sums of the positive ranks and the negative ranks will be similar. But if the sum is too small or too large, then you reject the null hypothesis. Okay. So back to the data here. So we showed the difference between the response time, and you first rank them, right, ignoring the sign. Just rank them by order of magnitude here. Okay, so the first one, the smallest magnitude is 1, the next is 2, and the third one is 7, and so on. So you ignore the signs here. Just rank the magnitude of the difference. And then you add the sign onto the rank. So here, the smallest value is the only one with negative sign. right? So now you have the sign rank of this is -1, and then the rest of them have positive sign. And then you sum all the negative ranks, which is 1 here, and then sum of the positive ranks, you have 77. Okay. Then so the p-value in this case is 2 times the probability of one of the sum is 1 or less. And then in this case, the p-value is 0.0098, which is less than the significance value. And in this case, when you use the sign rank test, the p-value is obtained by permutating the different possible combinations. Okay, so it's required a lot of computational power. That's why most people avoid using nonparametric tests. But now with computers, they make it a little quicker, but still it requires some computational power. So that's how you obtain the p-value. So in this case, you also reject the null hypothesis because the p-value is extremely small, right? And so we can conclude that there's a significant evidence that the medians are different between the 2 visual fields. And you can also calculate the confidence interval for this test as well, but it's very time-consuming and it's complicated. Okay. Most computer packages for exact tests can give you the confidence interval. So what happens if we ignore the pairing? So here, if we ignore the pairing and we want to use the sign rank test, or the equivalent test for independent samples of the sign rank test is the Wilcoxon test, right? So in this case, if you assume independent samples, the p-values from the 2-sample Wilcoxon test is 0.29, which is larger than the significance level that you set. So again, in this case, if you ignore the pairing in the data, then you will end up with a different conclusion. Okay? So that's why we need to be careful when we analyze the data, understand how the data was collected and how the study was designed. Okay, so the difference between the sign rank test and the sign test is, in the sign test, we didn't care about the ranking. In the sign rank test, we actually did look at the ranking, okay, and that affected test statistics. Let's say if you have an example where you have the sign test have 50% of the observations with positive sign, and 50% of the difference have negative sign, right? If you use the sign test alone, you would reject the null hypothesis. No, you would accept the null hypothesis, right? Because you have equal number of positive and negative differences, okay? But if you use a sign rank test, let's say all the positive have very high rank, and all the negative have very low rank. In that case, you might reject the null hypothesis because of the difference in the rankings. Okay? So in a sense, the sign rank test is more sensitive to the ranking of the observations. And like I said, it requires more power, more computational power to obtain the sign rank test. So the parity test, sign rank test, and sign test were used for quantitative measurements. Now, let's say we have qualitative measurements where the outcomes are measured as categories. To illustrate the example here, I want to use the data from a paper from Houlihan. And the data was published in the American Journal of Public Health in 1986. In this study, the objective was to determine risk factors associated with acute myocardial infarction in Navajo Indians. Okay. So the design was a retrospective match case control, and they chose this particular group of the Navajo Indians because they are the largest group that the data was available. And so they wanted to go back and look at different factors that can be associated with AMI, so acute myocardial infarction. Okay, so this data they collected, so it's a matched case control. So they selected 144 patients with AMI, and then they go back and look at 144 patients without AMI, and match them based on gender and age. Okay? And based on that data, they came up with the data shown here. For the AMA cases, there are 46 patients with diabetes, and 98 out of those didn't have diabetes. While the AMI controls, 25 have diabetes, and 119 have no diabetes. So they want to see if there's an association between diabetes and myocardial infarction. Yeah. So the hypothesis is there's no association between diabetes and AMI, and the alternative is there is an association. And here the outcome is categorical. And we use the McNemar test to test for the association. And the level of significance is 0.05. Okay, so McNemar test is used to compare proportions from two dependent samples. And what it compares is the pairs of discordants. Yeah. So in this case, if you want to test to see if the proportion of patients with diabetes in the control the same as the proportion of patients with diabetes in the cases, right? Comparing these two proportions is the same as comparing the off-diagonal elements, right? The off-diagonal proportions, because 25 is the sum of 9 and 16, and 46 is the sum of 9 and 37, so you have this common element. And so the difference in the proportion between these two can be obtained from the difference in proportion between these two elements, right? So under the null hypothesis, the off-diagonal terms will be nearly equal. Okay? If the off-diagonal elements are very different, then it means that there is an association between the outcome and the characteristics of interest. So the test statistics is a chi-square. You compare the difference between the off-diagonal element. So the test statistics is the square of the difference over the sum of the difference of the off-diagonal element. The inference is based on a chi-square with 1 degree of freedom. So back to this example, so the test statistic here, the total here is 144. But the test statistics, we only need to look at the off-diagonal elements, right? So the chi-square test statistics is 8.32. Okay? So the p-value is 0.0039 in this case. So again, this is smaller than the significance level, so we reject the null hypothesis. It means that we can conclude that there's significance evidence of an association between AMI and diabetes. Now, what happens if we ignore the parent? Okay. So in this case, as I explained earlier, the difference in proportion, that's what we want to test for, the difference in the proportion of diabetes in control and the proportion of diabetes in the cases, right? So because of the pairing, we know how many of the pairs have diabetes in both patients, or both subjects. If you ignore the pairing, then what you have is you have 144 observations with AMI, so 144 cases, right? And then you have 144 control. Okay, so we're comparing the proportion of 46 over 144, 25 over 144. Because you don't have any more information about the pair, so you can't say that, out of the 46 in this group and 25 in this group, 9 of them, both subjects have diabetes, right? So you lose that information. You don't use it in the test statistics if you ignore the pairing. So in this case, you have 288 observations, and you would use a chi-square test. And the p-value in this case is 0.041. So your conclusion in this example, by ignoring the pairing, your conclusion remains the same as the McNemar test, right? But this is an incorrect test. So, the previous two examples, when we ignore the pairing, we get a completely different conclusion. But that's not always the case, right? Sometimes you get the same conclusion by using the wrong test, but it doesn't mean that you should use the wrong test, right? Because you don't know when that will happen, okay? So I don't want you to go away and thinking, well, I used the wrong test, I will always get the incorrect conclusion. You might get the same conclusion, but that's not the right test. Okay? So in this case, what happened? So in this case, let's say no matter how many pairs that both subjects have diabetes, if you use the chi-square test, you get the exact same test statistics and same p-value. But if you correctly use the McNemar's test, your conclusion will vary depending on how many pairs that have the common outcomes, right? Okay? So this test is more sensitive in this case of detecting the difference in the proportion. Okay, so it gives you more information because you know more about the observations. You know who is paired with whom. So you have more information in these match or pair tests if you design the study to give you pair samples. Okay, so any questions? So in summary, in most pair analysis, you actually use, even though you have two samples, but because of their dependence, you actually look at the differences between each pair, right? So now you actually end up with only one difference for each pair. So you use a one sample test instead of two sample independent tests as before. And the test that we went over today was the parity test, which can be used for numerical measurements, where we can assume that the differences are normally distributed. And if the outcomes are numerical measurements, but you can't assume normality, then you can use the sign or the sign-length test. These are nonparametric tests. And if the outcomes are categorical, then you can use the McNemar's test. So if there's one thing you can take away from this talk today is if you design the study to be a pair study design, the data has to be analyzed as paired data. Okay? The study design will drive the analysis. You can't just take the data and not go back and look at how the study was designed and blindly do the analysis. Right? Any method can be applied to any data, but it doesn't mean it gives you the right answer. Right? I mean, it will give you an answer, but it might not mean anything, or it might not be correct. And for the first example, when we look at the laser and the cryotherapy paper, I looked at, there are two outcomes, right? The spherical equivalent outcome, which I use as the example, and they also look at the best acute visual outcome. In that outcome, they classify the data to good visual versus poor visual. Okay, so that becomes a categorical variable. But in the analysis, they actually did it as a chi-square test. So that was not right? Because they didn't take into account the pairing of the patients. They just treated it as independent samples. Yeah. So I didn't use that as an example here, but I was surprised because in the paper they say how pair t-test is the appropriate test, but then they completely forgot about it when they actually did the categorical outcomes, which was the primary outcomes of the study. Okay. So as a statistician, it's important for you to look at the design and make sure the analysis is done correctly.
What if I want to do a 1-to-n match, but the variable is continuous?
If you want to do 1-to-n
match, but the outcome variable is continuous, like in the parity test.
And the parity test.
Because in parity test, what you are doing is 1-to-1 match, right? Mm-hmm. What if I want to do a 1-to-n match?
That's actually more complicated. Actually, one of the things that we are doing for a grant is, how to look at tests that do 1-to-1 versus 1-to-n. Sometimes people actually average over the m observations in one of the group, and then do a parity test that way. Mm-hmm. And you can adjust for the test statistics using the weight, depending on the number of observations that you have in one group versus the other. So that's one of the ways you can do that. There,
Is there a table talking about this?
I can look for that. And one of the reasons that people don't use pair t-test, or not pair t-test, pair analysis is it's not always, it's not always clear or easy to calculate the covariance or the variance of the different test statistics. The dependence is sometimes hard to quantify. Okay, so there are plenty of tests that look at one-to-one. There are a lot of tests that look at continuous variables and categorical variable for uncensored cases. But when you look at survival time, for instance, that is actually more complicated. And especially if you look at competing risk data, there is very, very few methods right now that you can use to do a pair or match analysis. Is that your question? I look for the paper and then send it to you. Any other questions? So what if you overlook the pairing? What, like, in the pair t-test, if you overlook the pairing, you obtain the same mean difference, right? So, the difference itself is the same as if you ignore the pairing, as if you use the pair t-test. But because of the variability at the outcomes between subjects' variability, that's what you use to estimate the standard error of the difference, right? Because if you ignore the pairing, your variability is higher because you don't account for the commonality between the observations you get in each subject. Okay, so your variability is higher. So more than likely, in a pair t-test, more than likely you will end up reject the null hypothesis if you don't include pairing in the test. Okay? And then another thing is, if you ignore the pairing, then if you ignore the pairing, sometimes you can obscure the existing differences between the observations. Okay, so considerations for pair studies. If you do a pair studies, make sure there's no carryover effect. Make sure when you design the study, there's no carryover effect. And if matching is desired, only cases have the match control can be used. So that will affect your sample size. If you have a lot of patients, cases and you want to find match control for that case, and it's like the case is a rare patient, like a very old patient for that disease, for instance, you can't find a match control, then you will have to throw that patient out. So in the analysis, you have fewer observations. The matching is more useful in small studies. In larger studies, it's better for you to use regression method, so that way you can actually quantify the effect of the different variables. And use appropriate method to have other variables in the data, and then use appropriate regression techniques. And we do have we have the consulting service center, so if you need any help with designing the study or analysis or any questions, you can contact them. And they also have drop-in service, and here's the information. Any questions? Thanks for coming.